Right. Nick, I just added you as a presenter. I know this meeting is pretty much started now, but was wondering if you could speak or anything, if you have those controls.
Hi, yeah, can you hear me?
Mm-hmm.
And I see a button to share content if you need me to do that.
I have I'll be doing the slide deck if you guys want to, if
Yes.
that's okay, and you guys can focus on.
Yeah.
Perfect. All right.
Thanks.
Wait for some more people to join and we should be good. All right, looks like we are at time. I'm going to give it 30 more seconds to a minute and wait for more people to join, and we can get started here. I'll go through some housekeeping as well. All right, looks like we're a minute after. I'll just get started here with some housekeeping. Thank you everyone for joining today. I'm really looking forward to having this one and hearing everyone's questions and our presenters. Really quick, we are recording this meeting, so everyone is on mute for now. If you have any questions, please pop them in the chat. We'll have time after the presentation to answer all of the questions. With that, the recording and the slides will be distributed by the end of the week for you to have and review. And with that, I will pass it on to our first presenter.
Thank you, Kate. Hello, good afternoon, everyone. I am Saurabh Shikdar, working as energy engineer at ICF. And today I'm going to present our emerging technology study, energy modeling and analysis of dual fuel heating systems in single family homes. I'm going to present this study with Nick today. He's also there on the call. We conducted this study as a part of California statewide gas emerging technologies program. GET program is a collaboration between investor-owned utilities, primarily administered by SoCalGas, to identify and evaluate emerging and commercially available energy-efficient technologies. So as you can see on the screen, here's our team. ICF and Linkis collaborated for this project. Stephen is Director of Engineering at ICF and oversees overall project management For all gas ET projects, Nicholas and Crystal are from Linkis, and Nick is also going to co-present with me today. Next. Here is the agenda of our today's presentation. First, we'll go over the introduction and research objectives. Then we'll discuss our key findings from literature review and SME interviews. Then Nick will go over our energy modeling assumptions, associated methodology, and interesting Pareto plots and results associated with that. Lastly, we'll conclude our presentation with key project findings. So let's talk about dual fuel heating systems first. Dual fuel heating systems are commercially available. Still, they're considered as emerging technology. These systems contain a heat pump paired with an existing natural gas furnace and a smart thermostat. These systems offer flexibility to run either a heat pump or a natural gas furnace that is most emissions effective or cost effective. When the conditions permit, the system can choose to run on a heat pump, especially when the grid is cleaner. However, the system has the flexibility to run on a gas furnace when the grid is dirtier or during the coldest hours or peak winter periods. As you can see on the screen, dual fuel heating systems can be implemented in various configurations. This is one of that is replacement of AC with a heat pump and a smart thermostat. In another configuration, both existing gas furnace and AC can be swapped out and replaced with the system. In a third configuration, entire integrated unit of both gas furnace, heat pump, and smart thermostat can be retrofitted. The energy or emission savings of dual fuel heating systems are dependent on the switchover temperature, that is the temperature at which the operation changes from natural gas furnace to heat pump or vice versa. For example, if the switchover temperature is too high, it would reduce run hours of heat pump. This switchover temperature can either be static, that is solely based on outdoor air temperature, or dynamic, that is changing based on various factors. And there are several factors that affect the selection of switchover temperature apart from outdoor air temperature, such as grid emission signal, rate signals of gas and electric, and equipment efficiencies. As you can see on the figure, dual fuel heating systems with appropriate switchover temperatures can help avoid electric heating demand during winter peaks. There are three important terms which need to be discussed here, especially at the start of this presentation. Those are emissions balance point, economic balance point, and capacity balance point. As you all know, the capacity of heat pump decreases as outdoor air temperature decreases. The capacity balance point represents the outdoor air temperature at which the rate of heat loss from home equals the maximum rate of heat the heat pump can provide. Economic balance point represents the outdoor air temperature at which the operation of natural gas furnace would yield same operating cost as that of heat pump. Similarly, emissions balance point represents the outdoor air temperature at which the operation of natural gas furnace and heat pump would yield equivalent emissions. So yeah, these are the important terms, and we are going to refer to those in the later part of the presentation. Next. One of the main objectives of the study was to determine technical feasibility of dual fuel heating technology using a combination of Energy Plus models and spreadsheet analysis. The study aimed to determine the emission reduction potential of dual fuel space heating and analyze the impact of switchover temperature on total energy consumption as well as operating cost. One of the other goals of this ET study was to determine the cost effectiveness of installing dual fuel heating systems based on metrics used in California, such as TRC, which stands for total resource cost, and TSB, total system benefit. Next. Now let's go over key findings from our literature review and SME interviews. From literature review, we learned that about 47% of homes in US are good candidates for retrofit of AC with a heat pump. As per REX survey, which was conducted in 2020, we learned that about 60% of total homes in California have natural gas furnace as their main heating equipment. Recent study conducted by NEIA in 2023 demonstrated that there is a strong market demand for dual fuel heating technology in residential sector. Even though this is still considered as emerging technology, from our SME interviews, we noted that the adoption of this is pretty common in Northeast and Mid-Atlantic regions. As a part of this project, we interviewed about 9 subject matter experts working in this dual fuel technology domain. I think we have a couple of them on call today. Thanks for joining. From these SME interviews, we learned that some of the barriers in adopting this technology are lack of sophisticated control strategy or innovative thermostats, need of training of customers and contractors about best practices of installation. We also noted that there is one more important factor, which is difference in perceived comfort. As far as pre-qualifications for installing dual fuel heating systems are concerned, we noted that there are certain pre-calls which should be met, such as visual inspection of ductwork should be done, and associated thermostat wiring changes should be taken care of. And it's important to check whether the existing gas furnace is not too old or inefficient. As discussed before, there are several factors which affect this selection of switchover temperature and which play central role in determining energy and emission savings. And for that, now I pass it on to Nick for discussing our energy models and associated methodology.
Thanks, Rob. So let me first present our energy modeling methodology. We wanted to create a model based on a typical single-family home of among small homes, and it might not represent the average home, but it's meant to be representative. We used an off-the-shelf building model, which is used in California's deemed efficiency incentive programs, called the DEAR model. This slide presents some of the details about that model and the assumptions of the equipment. One of the aspects that we felt was important in this modeling was to capture the extremes of hourly heating usage. So whereas the DEAR models sometimes will aggregate over several variations of the home design, including orientation, number of floors, what we wanted to do was look at just one of those variations so that we capture those extreme temperatures. This variation we're looking at is the single story variation. It has a slightly lower energy use intensity for HVAC compared to other calibration data. And that's likely due to this slightly smaller window area, but it's still a reasonable representative home. We simulated, to handle the dual fuel heating, we simulated 2 models separately, one with a gas furnace AC combination and another variation with the heat pump. So these are 2 separate models. We then synthesized a dual fuel heating model from the hourly outputs from each of those 2 models, basically switching between operating modes in each hour. And we used the emissions factors and rate tariffs shown on the bottom right for gas and for electric. In certain parts of the analysis, we'll be talking about average rates. And then for comparisons, we're also using marginal rates, so the incremental cost to add 1 kilowatt hour or 1 therm, so that we can compare the control system making those incremental changes. Okay, next slide, please. So here are some examples of annual results using first pass, where we collected kind of overall information from these models and tried to filter out climate zones to focus on and kind of look at the range of possibilities. The left-hand group of columns under the heading Annual HVAC Fuel Cost, let's talk through those. The first column for the gas furnace is the gas furnace building. The next column over represents a building with just the heat pump operating, so those are not yet merged into a dual fuel system. Here we're comparing those to determine the next column over. If we choose between gas furnace and heat pump on the basis of annual cost or annual emissions, it shows us one or the other system being preferred. We analyze this in a spreadsheet with a control methodology to choose the system that was preferred. And you can see the preferred system based on minimum fuel cost is almost always the same as the gas furnace. I think this analysis refers to switching 1 hour at a time between the two systems. And essentially what we find is that if we're picking minimum cost, we almost always pick the gas system. And if we're picking minimum emissions, we almost always pick the heat pump system. But there are just a handful of hours out of the year where we might have picked the other one. So there's just a very slight difference in the outputs from this algorithm. The right-hand set of columns reviews if we look at, instead of minimum cost or minimum emissions, if we're looking at the annual results of emissions for one system that runs gas furnace all year, another system that runs heat pump all year, and one system that switches in each hour to the system with the minimum emissions. What we'd see is the preferred system method for minimizing emissions hour by hour is closely aligned with the heat pump control. There's just a very small number of hours that it would switch to gas furnace mode and save just a small amount of emissions. What this shows overall is that there's not an economic balance point or emissions balance point for this dual fuel model in California. And we'll talk about that on the next slide, please. This table showing emissions and cost savings using data from the previous slide. Continuing on with a spreadsheet analysis. The first column is the dual fuel emission savings using heat pump as a base case and looking at savings potential by switching. Second column is the same data reported in terms of percent. Third column over fuel cost savings with dual fuel system with the heat pump as a baseline. So here we're kind of discussing, with a given baseline, are there some savings percentages with the control design that was discussed in the previous slide. Also looking at cost savings as a percent of heat pump cost, cost increase for using a dual fuel system. That's operating cost increase relative to the gas furnace baseline, because the electric fuel, the heat pump system tends to be more expensive in most of the hours of the year. And then the last column represents the cost increase as a percentage of the gas furnace operational cost. So what you can see from this table is that the dual fuel system with the control described previously does not save much emissions relative to operating strictly as a heat pump. But you can see the cost to use a dual fuel system to minimize emissions or to use a heat pump is much more expensive. We used this analysis to down select to the climate zones we're going to focus on for an extended analysis, looking at these kind of ranges of cost and emissions percentage. We chose to focus next on climate zone 11 and 16. Climate zone 16 saved the most emissions and cost, or has the potential to, and climate zone 11 has the second most potential for a difference in cost and emissions between the dual fuel system and the baseline systems. On the next slide, we'll talk about those trade-offs a little bit more. Next slide, please. So in the previous spreadsheet analysis, we picked using kind of a simple question that said, in each hour, minimize cost or minimize emissions. We found that there wasn't a lot to compare using that metric alone. So in this slide, we looked at what's in between those 2 points. This plot shows the range of possible outcomes for annual operating cost and emissions in climate zone 16, depending on the controls, and thinking that there are options in between minimum operating cost and minimum emissions. Down at the bottom right, the green triangle represents the point where we operate all year for minimum cost, for minimum operating cost. It happens to be close to the outcome for operating in gas furnace mode all year, which is the blue circle. On the left edge, the red triangle represents controlling for minimum emissions all year. This control strategy outperforms the solo heat pump, which is the orange square, because the cost and emissions are lower. In between those 2 points, we've drawn a curve, a couple of different curves. The curve toward the top of the diagram showing temperature points represents if we run a control algorithm using switchover temperature controls, which is where the controller looks at the outdoor temperature, and if it's below a certain threshold, it runs the gas furnace. If it's above a certain threshold, it runs the heat pump. Excuse me. And the curve at the bottom represents the border line of possible other arbitrary controls that minimize emissions for a given annual operating cost, or vice versa. What we see is there's a difference between these two different curves, meaning the optimal type of controls can save a lot of cost to get to the same level of emissions. So looking at the gray line, for example, it just shows the difference between operating costs to get to that midpoint of emissions, which is halfway between a gas furnace and a minimum emissions dual fuel system. This is why we think it's important to encourage a optimal control type system that's aware of costs and efficiency in each hour, and to consider that controls when evaluating technical potential for the dual fuel heating system, seeing that there's a large discrepancy between an optimal control and a switchover temperature type control. Let's go to the next slide, please. This is a similar result for Climate Zone 11. Most of the same observations apply. One of the other things I can point out here is how the switchover temperature curve kind of converges with the optimal controls near the top left of the diagram. But the switchover temperature control never reaches the far left end, which is the minimum emissions. So it can kind of approach the that top portion of the curve, but we actually don't want to operate there where the emissions is about the same as the lower portion of the diagram, but the costs are higher. All right, let's go to the next slide, please. So here we looked at some of the hourly trends to try to explain or understand some of the factors that contribute to the results. In particular, we're thinking of how does the schedule of demand compare to the emissions factor for electric grid energy, and how does that affect the choice for which system is more efficient in terms of emissions. We saw that previously there was no economic balance point. Let's see, sorry, I skipped some. In the morning hours, that's kind of highlighted in the yellow box at the top left diagram for Climate Zone 16. We see in those morning hours, the emissions factor is not always low enough to prefer operating in heat pump mode based on emissions alone. This could be correlated to overall heating demand on the grid, and we note that converting all the gas furnaces to heat pumps will increase that demand, and that might have an impact on the emissions factor. On the other hand, in the middle of the day, there's a lower emissions factor, and that makes it a better time to operate in heat pump from the emissions perspective. However, based on this model, the model has a lower heating demand in that middle of the day period. And this is all at current levels, and we understand that the emissions factor will change over the coming years, and that might impact considerations later. On the other plot, we see there's kind of two peaks in the emissions, and the goal is to use heat pump to save emissions. You want to use heat pump when that emissions factor is high, but we'd like to point out that the demand for heating doesn't always overlap perfectly with when the emissions are high. Next slide. So going back to our spreadsheet results, we saw that there was no economic balance point, we called it, or emissions balance point, based on the current rates and emissions. And we wanted to consider if we diverge from the current operating costs and emissions factors, what are some of the other outcomes that we might see? So this question evolved as we worked on the research project. So what we considered here was to allow one of the parameters to vary, that is the rate the tariff rates for essentially the ratio of electric to gas, allow that to vary and see how it impacts our Pareto optimal curve. Another way of thinking of that is to vary the electric cost as a percentage relative to the current rates. So the orange solid line is the Pareto optimal front, showing the trade-off between annual operating costs and annual emissions or emissions reduction potential as a percentage of what can be achieved for minimum emissions. And we see that the more emissions you want to save, the more you have to put into operating costs, annual operating costs to move toward the heat pump. As the electric cost goes down, we have these other curves showing 80%, 60%, and so forth relative to the current rates. That curve flattens out, meaning you can achieve some emissions reduction, a higher degree of emissions reduction with a lower impact to the annual operating costs. And we estimated roughly 40% of the current rate, we would be able to achieve this kind of cost parity where you could essentially break even in terms of annual operating costs by switching between systems. And that could also occur if gas costs were to increase. It's kind of looking at the ratio. Next slide, please. So as a second parameter that we thought of to vary from current rates that might change the outcomes is if there were some sort of emissions reduction credit or other costs associated with emissions. And again, we're looking at that curve. It's flipped left to right. So now we're on the x-axis looking at emissions. And from the right side would be a reference for operating strictly the gas furnace. And each curve represents the range of annual outcomes for a given set of conditions, where again, you would choose one point on this curve to operate the system. And what we see is the top line, the blue dotted line, represents if there's the current rates with no emissions reduction credit. And as we increase an emissions reduction credit per ton of carbon emissions equivalent saved, the curve again flattens out to a point where there would be some point of cost parity where achieving emissions reduction could be achieved without changing the annual operating costs or with only a small amount of annual operating costs. In general, the same trend appears that for the first few units of emissions reduction, the incremental cost is lower than it is to save all of the emissions that's possible that we see in terms of the curve steepening toward the left. However, to get to the point of cost parity for the bottom line, the emissions reduction credit with current rates would have to be quite high compared to some other technologies that save emissions. Next slide, please. So here we looked into some of the other hourly parameters and other factors that again would influence the results. And essentially with different sets of assumptions, it's possible that we would get different results. So we're looking at, for example, the top chart shows essentially a result resulting from the performance curve of the system. It's comparing how much electric energy you would need to how much gas energy you would need to operate the system given outdoor temperature, and coloring that based on the emissions differential. So we do see that a lot of the emission hours with large emissions differential tends to be at cold temperatures, as we would expect when there's a higher amount of energy needed for running the heat pump. And then in general, this curve, the shape of the curve would reflect the assumptions in the model for the performance curves, which we did not modify. We just used, again, it was an off-the-shelf model, so that reflects the performance curves in the model. The second plot at the bottom shows a histogram of the hourly emissions factors. What we used was, for most of the calculations, the avoided cost calculator, which is a projection. And we compared that in this plot to watt time, which is a historical and real-time trending source. So that could, for example, watt time could be used to implement a controller that's aware of the emissions factor in each hour. And the histogram shows that there's kind of a similar shape, but at the right end, where the emissions factor is high, there's a little bit of difference depending on which data source we use. So the avoided cost calculator has more hours with very high emissions factors. The watt time data for the year of 2022 has more hours in that medium high range and not as many in the very, very high range. So year to year, the emissions factor histogram will change, and that could also impact the conclusions for annual results. Next slide, please. Now, Saurabh will summarize the findings.
Yes. Thanks, Nick. So this slide summarizes our key findings from the ET study, as discussed by Nick, with DEAR models and current rate tariffs in California and the modeling assumptions that we went through. We noted that there is no emissions balance and economic balance point in California. Gas furnace is almost always the preferred system choice for minimizing operating cost, and similarly, heat pump is almost always the preferred system choice for minimizing emissions. We also learned and understood the impact of rate ratio and emissions credit in making dual fuel systems cost effective in the state. Our analysis also highlight that limited energy and emission savings benefit can be accrued with the static switchover control strategy, and this in turn highlights the need of innovative thermostats which can optimize the switchover temperature based on several factors such as rate signals, emission factors, and outdoor air temperature. Input signal of outdoor air temperature on its own is not enough to achieve optimum performance for very high electric and electric to gas rate ratios and mild cold climate like California. As noted before, we also conducted cost effectiveness analysis and noted that TRCs were in the ranges of 0.6 for climate zone 11 and 0.5 for climate zone 16. Next. So we presented the study at several conferences this year. I presented paper on the study at ACEEE Summer Study in California, and I co-presented this with Nicholas and Crystal at ACEEE Hot Water Forum in Atlanta and ETCC Summit in Sacramento this month. So here are some of the pictures, and we got a lot of interest and questions on this topic at these conferences. Next. So yeah, this slide is about CalNext program. It's also a statewide program in California focusing on electric emerging technologies. I would encourage you all to visit their website for more information and their current projects. Thank you for patient hearing. And yeah, I saw a couple of questions in the chat. I tried to answer through text, but yeah, Nicholas, if you want to answer a question on rate tariffs as well as the table you had on slide 8.
Sure, if you want to go to slide 8, please. So the question was, why isn't the preferred emissions column the same value as exactly matching one of the other columns for gas furnace or heat pump? And should have explained a little bit more clearly. What we did in the background is we have an hourly calculation for each of these climate zones, where in each hour we chose one or the other gas furnace or heat pump. So it essentially is a dual fuel result in the preferred system. So what that refers to is the control method, choosing a preferred system in each hour in order to either minimize cost or minimize emissions. And so the result is somewhere in between gas furnace and heat pump, or in cases where there's an advantage to having a dual fuel system, might be a slightly lower cost or slightly lower emissions than one or the other. Hope that answers your question. And if we could go to slide 7, I see the other question was, it'd be really useful to know gas and electricity rates used. And yes, there's definitely a variety of those. What we assumed was we actually did 2 different analysis options for the electric rates. And in the bottom right, there's a table here. We looked at the gas side, just the typical rate tariff for each of the climate zones. We chose what we thought was the predominant utility serving that type of fuel and looked at their typical gas tariff. For the electric side, we did one analysis with a flat rate tariff and a similar analysis repeated with a TOU, time of use tariff. And we kind of chose what we thought were the most common. So if there was a default rate, we chose that. If there was a basic time of use rate, we chose that for the other analysis.
Yeah, and just would like to add one point. So we have we have mentioned average electric and natural gas furnace rates that we used in our analysis, which are climate zone wise. And I think you can find that in our final report, which is uploaded on our website. Thank you.
Thanks for those questions.
Yeah, next event date is not finalized yet, but stay tuned for our communication regarding date, time, and topic for that.
Any further questions for the 2 speakers?
I think just one got dropped in the chat just now.
Yes. So the question, I'll read it from an operating cost standpoint, how do the cooling savings from an efficient heat pump factor into the analysis? Which is, it's a great question. What we're assuming here is, in our analysis, we only looked at the heating energy, heating mode. And you raise a good point that when you're replacing the air conditioning system, you have a chance to install more efficient cooling option. But you can also, I think what we're comparing is, assume you're already going to replace that air conditioning, and you have a choice between a new efficient air conditioning or a new efficient heat pump. And so there will be some cooling savings either way, whether you put in an efficient air conditioning or put in an efficient heat pump. But that's a great point, that there will be, usually when you replace the old equipment, there's going to be cooling savings as well. We didn't analyze that in this project.
And there was one more question that Gray.
Yeah. Yeah, for cost effectiveness analysis, we considered the equipment cost, like equipment replacement cost, estimated level, which was shared during SME interview milestone. But for other analysis components, we primarily focused on annual operating cost.
See another question. Did we present this to the CEC for the Title 24 code? For example, they take case studies to propose changes to the code. We didn't present it. I think we were a little bit after the case studies for the 2026 cycle. And most of those case studies are regarding new construction. So I think the intent of this study was to look at existing homes that already have a gas furnace. And it's a little bit unclear, how that would factor into the Title 24 code. It would have to be under major renovations. But no, we didn't submit a case study.
Yeah, to answer to your question on significant changes in the presentation after ACEEE, yeah, primarily, I think we changed a couple of plots in this presentation, especially in the initial part, which had the conceptual switchover temperature. But yeah, apart from that, no major changes.
Other questions for Nicholas or Saurabh? If not, just want to thank both Nicholas and Saurabh for their presentations and appreciate you all attending today.
Yeah, thank you for the questions and stay in touch with us. You can see our LinkedIn page and our website information here. Thank you.
Bye.
Thank you.
Thank you, everyone.